This meeting is being recorded.
In section 5, we're going to discuss the ratio selectivity regarding halogenation. So we're going to start with chlorination and look at what region, what area of the molecule will be halogenated, and I'll compare that later on to bromine. So substrates, if you recall, so an alkyl halide, for example, is a type of substrate. When we have things like ethane, multiple halogenation sites can be proposed or will be possible. So even though we're just talking about monohalogenation, we can still have multiple products in addition to multiple chlorinations that can occur. So when we have this product, we could see a secondary site through halogenation or a primary site with this halogenation. So significant amounts of both of these products would be obtained. And this has to do with the relative potential energies between a primary and secondary radical. So what we see here is that there's not much difference in energy during this rate determining step, this creation of the site of chlorination through hydrogen abstraction. And we see that the secondary carbon will be faster because it's lower energy than the primary carbon. So that's why we have this slight difference in percentages because of this one being a little bit slower, and this will be our faster one because of the lower energy. But they're still pretty close in relative energy at that transition state. So we might see this distribution of 60-40 with secondary site radicals and primary site radical chlorination products. So in general, chlorination is much less radioselective than bromination because of this smaller energy difference and overall faster reaction to go from reactants to our transition state. So let's look at bromination here. It's a much slower reaction, and it will be much more selective than for a secondary carbon site because of that lower potential energy. So we see a secondary bromination about 97% of the time compared to a primary bromination. So it is much more radioselective than this chlorination. And if you recall, Hammond postulate, we'll walk through these next couple of slides quickly and then talk about the important stuff here. So Hammond's postulate told us that if a reactant is closer in energy to the transition state, then our chlorination product will resemble, or our chlorination intermediate here would resemble our transition state. And then if we have over here our intermediate that results, our transition state resembles our products a little bit more with bromination. And this is again that Hammond postulate. So the closer in energy to the transition state is what your transition state appears. So either as a reactant or with the bromination, the transition state is closer to the intermediate. So it would resemble our product more. So we'll jump to the next slide here. This specifically was the rate determining step, though, you should note, as our hydrogen abstraction shown here. And this representation, you really don't need to know the details too much about, but again, this is showing the difference in rates and radioselectivity of chlorination versus bromination. Let's go to our next slide here. Again, it's really the stability of the transition state that factors into our final product. And this slide here is much more important to review. We're told in short here that this difference in transition state energies for the formation of a primary, secondary, or tertiary radical, the difference between these is much larger than it is for are chlorination. So see those differences in energies at transition state versus these large differences here. So again, the rate determining step of hydrogen abstraction is going to be much faster, right? This rate of chlorination here than a bromination. And then since this is much slower, the lowest energy will be more highly selected. So the tertiary bromination, the tertiary radical site bromination will be much more selective for that, based solely on this lower energy pathway. So let's take a look here at what can happen in the overall bromination versus chlorination if we have the possibility of a tertiary site versus a primary site. So at the tertiary site, when we have bromination, this really occurs pretty much at 100%. And that's because if we were to say, relative reaction product concentrations, if this was one, this would be about 1,600 times more often. So that's what we're told here. So this 1 to 1,600 gives us this 0 to 100% ratio of our primary to tertiary product. So you can just assume that if you have a tertiary radical site possible, bromination will occur there. But with chlorination, we still see that tertiary site versus primary site in this 65-35% split. So overall, we can see a summary here on this last slide of fluorination, chlorination, or bromination. Iodination is just really entirely too slow compared to these other reactions. And fluorination, on the other hand, this is very fast and the least selective of either of these processes. So that's where you see the largest, more equal, I should say, distribution of a 1 to 1 to 2% ratio, rather. So 1 to 1 to 2 to 1 to 4 with a fluorination. And then chlorination, right? We saw, well, on our last slide, it was like a 35-65% split, but you can see that it's definitely more favorable for the tertiary compared to fluorination. And then bromination, this is our last comparison here. And this is why we say from primary to tertiary, it's really 0 to 100% tertiary with bromination. So most selective, bromination. Least selective, fastest pathway overall, fluorination. And then chlorination we know is just less selective than bromination overall.